Thanks very much for the invitation. It's a great honor to be talking here. So let me start. So K is going to be a field. And C over K is going to be a smooth algebraic curve. And omega 1 will denote sheaf of differentials. So C is always going to be equipped with V, a vector bundle, and we'll denote by M its sheaf of sections. So we call that a connection is a map, is data of a map, nabla, from M to M tensor omega 1. And it's not going to be linear. What happens is it obeys some sort of Leibniz rule. And over here, M is going to be a section of the vector bundle, and F is going to be any function. So this data is the same as the following. So given D, a K derivation on OC, the connection can be contracted with D to give a map from M to M. And now the Leibniz rule is going to change to nabla D of Fm is F times nabla D of M plus D of F times M. And what we're going to be mainly concerned with is solutions to such vector bundles with connection. So we say that M in a section of the vector bundle is a solution if M is in the kernel of nabla. So this is the same as saying that for all derivations D, you have nabla D of M is 0. So we say that the vector bundle with connection has a full set of solutions. In fact, let me say rational solutions if the solutions span M as an OC module. So maybe I should say that if M is a solution, then nabla of F times M is going to equal M times dF. And so the solutions are not going to be an OC submodule of M. And we say that the vector bundle with connection has a full set of algebraic solutions. If you have a full set of rational solutions after taking a finite pullback of C. And the question is, given a vector bundle with connection, can we come up with an arithmetic criterion that tells us when it has a full set of algebraic solutions? So to talk about this, let's first see how solutions look in certain cases. So let's take the case when K is the field of complex numbers. So we're looking at solutions over C. So given a vector bundle with connection on a curve over C, by looking at complex points and by treating it as and by looking at the complex topology, one gets a Riemann surface and a holomorphic vector bundle with connection. So now we're going to think about the vector bundle with connection as holomorphic data, not as algebraic data. And the thing about holomorphic solutions is that they're a lot more easy to come by. In fact, they always exist locally. So if you take U, which is going to be a simply connected open set of C and, then if you pull back V and nabla to U, you'll always be able to find a full set of solutions, holomorphic solutions. In fact, the sheaf of holomorphic solutions will be a local system for the analytic topology in C and. And these are in correspondence with representations of the fundamental group of your Riemann surface, C and. And having a full set of global holomorphic solutions is going to be the same as saying that this representation has trivial image. And having a full set of a full global set of holomorphic solutions after finite pullback is going to be the same as saying that this representation has finite image. And so if you were to have algebraic solutions, so if we were to have a full set of rational algebraic solutions, then of course you will have a full set of analytic solutions, and that's the same as saying that your representation is trivial. And now asking for a full set of algebraic solutions, in other words, solutions after finite pullback, will imply that the representation has finite image. But again, what we're concerned with is the existence of algebraic solutions. So we are actually looking for arrows that go the other way. And as it turns out, if you insist that your vector bundle with connection has regular singular points, then having analytic solutions is going to be the same as having algebraic solutions. So I'm not going to define what it means for a vector bundle with connection to have regular singular points. But as later on, we will assume certain arithmetic inputs. And the theorem of Katz tells you that once you assume those inputs, these conditions are always going to be true. And so we'll only be concerned with computing monodromy. So this representation is going to be called the monodromy representation. OK, so that's what happens in characteristic 0. So as it turns out, things behave quite differently in characteristic P. And let's see how. OK, so let's assume that P is 0 in the field K, in other words, K has characteristic P. So then first of all, you will end up having many more solutions. Note that if M is a solution, then nabla of f times M is going to be M tensor df. So in particular, if your function happened to be a pth power, then df is going to be 0. And this is because d of f to the m is of f to the p is 0. Excuse me. And in particular, the solutions are going to be an OC twisted by Frobenius module, which is again very different from what happens in characteristic 0, where you have solutions being a local system and not a quasi-coherent module. And in fact, there's actually a very nice criterion that tells you exactly when you have a full set of solutions. And in order to do that, let me define what's known as the p-curvature of the vector bundle with connection. So the p-curvature, psi p, is defined as psi p is going to take a derivation d, and it's going to spit out the following object. So in characteristic p, if d is a derivation, so is d to the p, and it makes sense to look at nabla of d to the p, which is going to be an endomorphism of m. And you could also look at nabla of d and raise it to the p as an endomorphism of m again. And that difference is defined to be the p-curvature. And it's a theorem of Cartier that says that you have a full set of solutions exactly when the p-curvature vanishes. It should be 0 for every derivation d. So if that happens, then you will have a full set of solutions. So that's what happens in characteristic p. And the conjecture is that if you start off with something in characteristic 0, and if you know about what happens modulo p for all but finitely many primes p, then we expect to know what happens in characteristic 0 as well. So the conjecture is due to Grothendieck and Katz. So now we're going to assume that the characteristic of k is 0. Let me write that over here. And the conjecture says that if you have a full set of algebraic solutions in characteristic 0, that is the same as saying that you have a full set of solutions mod p for almost all primes p. And by Cartier's theorem, that's the same as saying that mod p, your p curvatures vanish for almost all but finitely many p. OK. So by what we said, by what was written earlier, saying that you have a full set of solutions in characteristic 0 is the same as saying that your monodromy representation is finite and you have regular singularities, and it's the theorem of Katz that says that if your p curvatures vanish for infinitely many primes p, then your vector bundle with connection has regular singularities. And so the conjecture therefore reduces to showing that if your p curvatures vanish for almost all primes p, then you have finite monodromy. So the whole thing boils down to a monodromy question. So let me just rephrase the conjecture. So the theorem that I want to talk about today is the following. So if C over K is a generic curve, and I'll define what this means. I'll define this precisely in just a minute. So let's say let C over K be a generic curve. Then the p-curvature is vanishing for almost all primes p implies that every simple closed loop has finite monodromy. So I can't say anything about the entire monodromy representation, but what we do know is that every simple closed loop will act with finite order in the monodromy representation. So let me make a few remarks about this and about related things. So first of all, what does it mean when I say C over K is generic? So let C be genus G with D punctures. So I mean, so C is going to look like a compact, proper, smooth genus G curve for some G, and we assume that there's going to be D punctures in C. So we're not assuming that C is going to be proper. So then the data of C over K is going to give you a map from. So this is going to induce a map from spec K to the moduli space of genus G curves with D marked points. And we say that the curve is generic if the image of this map contains a generic point of MGD. And over here, we're going to think of this as a co-scheme over Q. So we say that's generic if the image of eta contains the generic point of MGD. And as it turns out, this assumption is very strong, at least very important for the proof, because if the curve
minus 3 points is generic.
Yes, and then that just gives back your theorem for local monodromy. All right, so if you didn't assume, if this generality condition was not could be relaxed, then that would imply the whole p-curvature conjecture. So by relaxed, here's what I mean. If given v comma nabla over a C, which is defined over a number field, if you could somehow extend it to a generic curve, and by doing so, you could also ensure that the p-curvature has vanished on the curve, on the vector bundle with connection over the generic curve. If this could be done, then that's the same as relaxing the generality condition. And doing so would imply the whole conjecture. And here's why. If you had any element of pi1, which was not a simple closed loop, then you could pass to a finite cover of C so that the non-simple closed loop becomes simple closed, and then apply the theorem. You see that that has finite order. And so the thing below would also have finite order. And if every element in your fundamental group had finite order, then that would imply that the image was finite, which is why this assumption is key.
If every element in the group is a finite order,
then it needn't be.
no, every element is finite order.
Yeah, it's a Bernstein problem. Needn't
but it's, I think, because this is finitely.
Not bad groups,
Right. Yeah,
You
these.
have every element. You have these special elements. I mean, simple class.
Oh, no, I'm saying.
Yeah, if you pass to a cover.
If you pass to a cover, so relaxing this condition would mean every element would have.
I understand your main theorem, how close you are to showing every element that's finite order without passing.
Not at all.
No.
Yeah, no, I need simple close very, very strongly, as you'll see.
Yeah, what's this argument that, so you have this finitely generated group,
Mm-hmm.
and maybe you can think of it inside GLN,
And
every
if,
element has finite order.
I think Burnside's, this is a theorem by Burnside that tells you that under these conditions, the group has to be finite.
It's linear.
Yeah, it's contained inside. It's contained inside GLN. Okay. So as it turns out, this isn't going to be enough to prove the conjecture for generic curves, because there are examples of representations of these fundamental groups, so that every simple closed loop has finite order, but the entire image is infinite. And you construct these representations using topological quantum field theories. So this is done by Thomas Kobada and Ramanujam Sentaru-Bain. They construct representations of these fundamental groups such that every simple closed loop has finite order. But the image is infinite. In fact, I think they also do this with bounded order. And this theorem can also be you can replace finite with bounded. So that's not going to prove, that's not going to give the conjecture for generic curve either. Okay, and now before going on to the proof of this theorem, I want to talk about an example, and it's that of GM. Because there's a very nice calculation done here, which is due to Katz. So GM is going to be spec of K T inverse comma T. This is due to Katz. Okay, so GM is spec K T inverse T. We'll always work with a particular derivation, and it's not going to be d by dt, but it's going to be t times d by dt. And the reason for this is, if you look mod p, d of t to the n is going to equal n times t to the n. And so d to the p of t to the n is going to equal n to the p times t to the n, which is nothing but n times t to the n. And so mod p, d and d to the p are the same. And this just makes computations a whole lot easier, which is why the slightly curious choice of d equaling t times d by dt. Okay? And I'm only going to talk about the case when the vector bundle is actually a line bundle. And let the sheaf of sections be generated by epsilon, which is going to be a non-vanishing section. Okay. So now, given that the p-curvatures vanish, let's see how one constructs an algebraic solution. So using Katz's theorem on regular singularities, let's assume that nabla of d is going to equal nabla d of epsilon is going to equal lambda times epsilon, where lambda is actually a constant function. And now here's how you use the fact that the p-curvatures vanish. Let's say mod a prime frac p. So nabla of d to the p of epsilon is going to equal nabla of d of epsilon, which is lambda times epsilon. And because lambda is a constant function, nabla of d whole to the p of epsilon is now computable linearly. And this is going to equal lambda to the p times epsilon as well. And assuming that the p-curvatures vanish is the same as saying that these two things are the same. So you have that lambda to the p is equal to lambda mod p. And this means that if you look at the number field q lambda, it's going to be, so this means lambda mod p is going to lie in fp. And so q lambda is going to be split at almost all primes p. And by the Chebyshев density theorem, this is going to tell you that lambda is a rational number.
This suggests that maybe the conjecture shouldn't assume all p, but just much less. That's something
You are asking the ST1 over Q?
What?
You are asking like not assume almost all P?
Yeah,
Yeah,
in
there's
the
some
converse, can you
formulation.
assume much less than
You still need something like density 1.
just this? Yeah.
Oh, what about density bigger than half? Will that be, do you think that'll be enough?
I guess, but
OK.
when would you ever
No,
experience
density
it
more
in
than
life?
half is not enough. Oh no, I didn't know.
Strictly more than half. I see.
I wasn't asking. I was asking if somebody formulated it in that form.
I think
not
Andrew
necessarily.
mentioned it was one of his papers that density was maybe enough.
I see. OK. So so given this, so this means that q lambda equal to q, and so lambda is going to be a over b, wherein b are integers. So then it's an easy check to see that t. So now look at epsilon 1. Choose a different section, which is going to be t to the minus a over b times epsilon. I'm going to put this in quotes. Is going to be an algebraic solution. So if you look at nabla of d of epsilon 1, that's going to equal t to the minus a over b times a over b times epsilon plus minus a over b times t to the minus a over b times epsilon. So this is the linear term. This is the Leibniz term. They cancel. And you see that epsilon 1 is an algebraic solution. So I've inverted. I'm now extracting. We're extracting roots of t. That's the same as saying you pass to a finite cover of Gm. And once you go there, this function becomes an actual function. Once you pull back to the finite cover, your line bundle with connection has a full set of rational solutions. OK. So that's the proof for, let's say, line bundles over Gm. And for the rest of the talk, I want to talk about the proof of this theorem.
What was the theorem of Katz that you mentioned with the function 3 minus 3 points? Is the conclusion the same as yours or stronger?
I think it's, well, in the sense, I think it's the same conclusion, because any simple closed loop is just going to be local monodromy. And Katz proves that if the p-curvatures vanish, then local monodromy is finite. Any other questions? OK. So as I mentioned before, we will need to use the assumption that the curve is generic. And here's how we do it. If you have a generic curve, then it's possible to spread out to a family of curves. And then I follow a beautiful suggestion of Emerton and Kisson, which is to use the fact that if you're OK, so once you have a generic family of curves, then every simple closed loop can be contracted to a node by passing to the boundary of the base. And it was a suggestion of Kisson and Emerton to use the fact that these smooth curves degenerate to nodal curves at the boundary of your family. So here's the exact technical theorem that prove. So let's say you have a base, let's call it B bar, and you have a family of curves over the base, C over B bar. And let's say that this family is smooth in some open B. And it's called so this is going to be B bar minus B. So this is going to be a point in the smooth locus. Let's say the curve, the fiber over the smooth point is a curve like this. And let's say the fiber over singular point is a nodal curve. And let's say that you get from the smooth curve to this nodal curve by contracting to a point, by pinching off to a node, this simple closed loop. So gamma contracts to the node of a singular fiber. So then the theorem is that if almost all p-curvatures vanish, then the class of this loop has finite monodromy. And then you notice that if your family is a generic family, then every single simple closed loop can be pinched off to the node by choosing an appropriate degeneration to some boundary component. And so you can say that every single simple closed loop has finite order in the monodromy representation. And the way you prove this theorem is to study the whole picture in a neighborhood of the node. So in a neighborhood of the node, in a local neighborhood of the node, holomorphically, you're going to look like a family of annuli, which will contract to a nodal curve at the nodal fiber. And the hope is to somehow use the fact that annuli are nice because it sort of looks like GN. But the problem is this is totally holomorphic, and at least as stated, there's no way to use the fact that the p-curvatures vanish. So what I do is I study a formal neighborhood of the node, which is going to be a rigid analytic annulus over some equicharacteristic zero base, and then prove that for such annuli, some sort of p-curvature theorem holds, and then from there deduce that the holomorphic annulus also has finite monodromy. So deducing that the holomorphic annulus has finite monodromy from the rigid theorem isn't too hard, so I'm not going to talk about it. I'm going to spend the rest of my time talking about the rigid theorem. So let me set things up for that. So I said something about having an equicharacteristic zero base over which we'll have a rigid analytic annulus. then you look at the power series ring in some variable q with q inverted. So this is going to look like the base. So what we do is we start off, I'm sorry?
C1 over n, bracket, what?
So this is power series in Q.
Oh, it's double bracket.
It's a double bracket, sorry.
It's not the absolute value.
Oh, no. OK. OK. So the cube over the node, the rigid cube over the node, is going to be some annulus with positive radius with special fiber and nodal curve. In fact, special fiber is going to be the node. And what one does is to change coordinates slightly, to change integral model so that it extends to a nicer, so that the vector bundle with connection will now extend to the special fiber. So here's here's the annulus we'll be working with. So the annulus is going to be, let's call it x, with inner and outer radius 1. So this is what happens when you change coordinates and you look at a subannulus with consisting of elements with just consisting of the radius 1 part. And let's say the annulus has coordinate t. And we'll again work with the special derivation t times d over dt. So in these coordinates, the ring of rigid functions is going to look like z1 over n power series q with q inverted t inverse comma t, where this consists of all Laurent series. So let's say an t to the n, where your indexing set runs over all integers, such that the q-adic valuation of your ans goes to infinity when your coefficients when your n either gets very large or very small. So as the absolute value of n goes to infinity. So this is going to be the ring of rigid functions on such an annulus. So here's the theorem. So let V comma nabla be a vector bundle with connection on X along with a cyclic vector. And this is a harmless assumption, because given our setup, we can always choose an annulus so that you have a cyclic vector. And such that almost all p-curvatures vanish. Then the vector bundle with connection in terms of the cyclic basis will extend to the special fiber as well. So in other words, there's going to be no denominators in Q. So with respect to the cyclic basis, the connection matrix extends or has entries in z1 over n power series in Q, no longer Laurent series, and then after finite pullback, you have a full set of solutions, but in order to do that, you might have to invert infinitely many primes. So let me say script x base change to q has a full set of solutions.
And that base change means you now have Fourier series in Q. You're not just tensoring over Z with Q. Or what do you mean by the base change?
Yeah, so I mean I replace Z1 over n by Q. But again, to deduce holomorphic solutions, that's OK. I'm not going to sketch the proof of the first part. I'm just going to maybe say a few words that will hopefully convince you that it's true. So like I said, this rigid annulus over this base should be thought of as a family of should be thought of as a formal version of a family of holomorphic annuli over the punctured unit disk, and the punctured unit disk because you are inverting Q. Now, if we all believe the p-curvature conjecture, we should believe that you have finite monodromy over all fibers, and because everything here's the calculation that goes into proving the second part. So now the point is, once that we have extended everything to this base, we can start reducing mod high and high powers of Q. And note that the special fiber of this annulus is actually going to be Gm. And we know the p-curvature conjecture for Gm. And so as you mod out by high and high powers of Q, you sort of just get thickenings of Gm. And so hopefully you can do something about it, because Gm is a nice space. So here's exactly how the calculation goes. So let's say nabla of D of the cyclic basis epsilon is A times epsilon. So this is the cyclic basis. And this is going to be a matrix valued in, let's say, Z1 over n, power series Q, T inverse comma T. So what we'll do is we'll change basis and bring it to regular singular form. In other words, we'll work with a different basis where A now will not have any powers of T in it. And here's how you do that. So note that mod Q, you have Gn, and we know the theorem for Gm. So let's take a finite pullback. So you have a full set of rational solutions. That just corresponds to taking roots of T, which is OK. And let's assume that we've passed to a basis so that A is going to be 0 mod epsilon. So after finite pullback plus change of basis, we assume that A is going to be 0 mod Q. Now, using an inductive argument, we'll show that A can be made constant. And once we do that, we'll use the p-curvatures vanishing to show that A will actually be 0. OK. So mod Q to the n. So let's assume that mod Q to the n, A is going to be 0 mod Q to the n. Sorry, let's assume that A is going to be constant mod Q to the n. So we assume that A is constant modulo q to the n. So mod q to the n plus 1, here's what it's going to look like. Let's say A is going to be q times c plus q to the n times b of t, where b of 0 is 0. So what we do is we take out the constant part of b, and we write it as q times c. And we take the rest of b, and we take the rest of it and call it b. And the reason we do this is because with respect to the derivation d, things of this sort can be integrated. And you can maybe hope to make it 0. So let's choose b1 such that d of b1 of t is b of t. So then pick your next basis. So let's say epsilon prime to equal the identity minus q to the n times b1 of t times the previous basis. And we'll show that with respect to the new basis, the connection matrix is going to be constant mod q to the n plus 1. And then the same inductive argument will apply to show that the connection matrix can be made constant without modding out q at all. OK. So now this is just going to be.
Does B1 exist?
I'm sorry?
Why doesn't this B1 involve a lot of denominators? Choose B1 such that.
Sorry, denominators in what? In q or in t?
I don't know. I'm asking you.
Oh, well, so b of 0 is 0. And so b of t is just going to be something like a polynomial in t, where a0 is 0. Integrate. OK, so if this was b, then b1 would be an over n times t to the n.
And that division doesn't hurt you in this setup where
No, it doesn't. But you, as you see, you do start inverting primes, but only finitely many.
because B was a polynomial.
Because b was a polynomial. OK. So epsilon 1 is going to be the identity minus q to the n times b1 of t epsilon. And now if you do the computation, you see that nabla of d of epsilon prime, that will equal q times c plus. OK. Let me spare you the computation. And you see that you just end up with q times c times epsilon prime. Things cancel out exactly to tell you that this new basis epsilon prime won't have any t's modulo q to the n plus 1. And for that, we do need the fact that c is 0 mod q. That is important. OK. So now we have that A is going to be an element in Mn of Q power series in little q. And this is because, like I said, in order to go from b to b1, you need to invert primes. And as n becomes bigger and bigger, you might have to invert more and more primes. And so in the end, you might end up inverting every prime, which is why A is just going to be an element here. Though I do suspect that you should still be able to find solutions without inverting infinitely many primes. But anyway, we don't need that for the application. But the thing is, mod q to the n A will be in Mn Z 1 over n q, because at each step you only invert finitely many primes. And so mod q to the n, not only do you have that A is going to be integral, you also have that your p-curvatures vanish for all but finitely many primes, though that finite set might grow as little n grows. Still, let's say bigger than 1. Q to the n for large enough p, you have that the p curvatures vanish, and that gives you that a to the p is going to be equal to a. But note that a is a multiple of q, because we've assumed that mod q you have solutions. And so for large enough primes p, in fact for p bigger than n, a to the p is going to be 0 mod q to the n. And so you have a is 0 mod p and q to the n for all primes large enough. And this implies that a is 0 mod q to the n for all n, so it has to be 0. So this sort of tells you that you do have a full set of solutions once. So you do have a full set of solutions, of rigid solutions, and from there, showing that you have a full set of holomorphic solutions is easy, and that proves the theorem. So I think I'll stop here.